So hello everybody, and welcome to the third week of our seminars here in the program on kinetic theory. Today we have two speakers, and first one is Josephine Evans from Warwick, and she is going to talk about the Goldstein-Taylor equation and what type of thanks.
Okay, so this is a joint work with Helge, so please direct any questions to him. Yeah, no, actually, I'm slightly nervous to talk about this rather than Helge talking about this, because in the end we solved everything with spectral theory, which is much more stuff he knows about than me. But I will tell you, I think, okay, so the general question we're trying to look at is if we have a kinetic equation that looks like this. So I guess you're all used to, so we have some transport and a linear collision operator. And then the unusual thing is here we have a spatially dependent jump rate. So how fast you're colliding, or your Fokker-Planck part, or your linear Boltzmann part, how fast these jumps happen, or how big your diffusion in V is, depends on space. And it's encoded by this function sigma x. So there's been a few works about this these kind of equations recently, so they're a challenge to do with standard hypocoercivity techniques. A lot of things break down when you have this dependence in x of sigma. And there's been a few works about them recently, because you have to develop some new techniques. But the question Helge and I have been working on is slightly different.
I'm not sure if she's.
Can you
Okay.
from the room?
Shall I try and mute them?
I think the IT services will.
Okay, I don't know how to.
I'm mentioning us. I don't know. Maybe they might need us. What microphone did you let it set on? The laptop one or the big one? Because you sometimes have to switch it here, you know?
I don't have one.
Yeah,
I don't know.
I said it.
No, they fix it. Don't worry.
Okay. So the question Helge and I were looking at, asking about these types of equation is how can we choose sigma to get the fastest rate? Of convergence to equilibrium. So normally with one of these hypocoercive problems, you fix your sigma of x, and then you say, can I bound the rate of convergence to equilibrium? And instead when you have this sigma present, anyway in hypocoercivity, you tend to get very bad bounds on your rates of convergence to equilibrium. And when you have this sigma present, there are very few quantitative bounds, and basically no one writes down what they are. So we wanted to find, so there's a couple of motivations for this. We wanted to find another way of understanding how the rates of convergence depend on their quantities in the equation. So if you cannot compute the optimal rate for each sigma, you can still see something about how your rate of convergence is depending on sigma by looking at which one will give you the fastest, or which one will give you very slow rates of convergence to equilibrium. So there's some more kind of practical motivations. So the first one is to try and speed up. Sorry, I can't write very neatly on this. Can we speed up MCMC schemes? Some of you probably know very well, and maybe others of you have never heard, but often these kinetic equations above, when you have a confining potential, are used to sample from some log concave distribution that you get out of doing Bayesian estimation. So you find you have whatever your target distribution is that you want to sample from, you construct a Markov process which has it as its equilibrium state, or in kinetic theory as its x marginal of the equilibrium state. And then you run your Markov process in order to sample from this. If we introduce a sigma x here, we won't change the x marginal of the equilibrium state in most of these nice cases. And so if we can choose a sigma x that makes you go to equilibrium really fast, sigma of x that makes you go to equilibrium faster than amongst constant sigmas, then we can make a slightly more efficient algorithm for doing our Hamiltonian MCMC. And then I guess there's a third thing is that, I mean, maybe this is a little bit of a stretch, but real systems look like this. And you care about choosing your jump rate in a way that will make the convergence to equilibrium fast or slow. So an example of that is nuclear reactors. So if you have it will be a nonlinear equation, but if you have the neutron transfer equation, it will be of this form, and this sigma x will be really big where you have the control rods in your nuclear reactor and basically zero in other places. So having an understanding of, in practice, these people have an understanding of, stick the nuclear reactor, the control rods in and it falls down. So maybe it's not really an important maths question to work out exactly how cool it will get when, but there are, I guess, so this is kind of the three reasons we want to understand more about how the rate of convergence depends on sigma of x. Understanding more about hypocoercivity, MCMC, and then there are some models where this is kind of more or less the structure of the real models, and we really care about the rate of convergence to equilibrium. And I think there can also be related questions. So if we have a spatially inhomogeneous kinetic equation on a bounded domain, say with specular reflection boundary conditions, then the rate of convergence depend on the shape of the domain is a kind of interesting problem. Okay, it's a hard problem to work out how to think about, and we have not solved it, so don't get. But you may know the Faber-Cran inequality, which says the spectral gap of the Dirichlet-Maxwellian, not Maxwellian, Laplacian. The spectral gap of the Dirichlet-Laplacian is maximized on circular domains. So if you have a kinetic equation, if you want to do, Faber-Cran but kinetic, you want to know what kind of shape, if you choose a boundary condition, what kind of shape of domain would maximize the spectral gap or the rate of convergence to equilibrium of your. So this is, I guess, we expect that maybe you can treat the kind of problem of working out how to optimize the shape of the domain in a slightly similar way to working out how to optimize this sigma x. And you might get similar kind of results. So, that's very speculative. We haven't really managed to do anything about that yet. But I guess just to motivate it. So some background about the previous works. I don't think anyone has really tried to answer the questions about optimizing the spatially dependent parameter to produce the fastest rate of convergence to equilibrium, but there are quite a few works about these equations with spatially inhomogeneous jump rates. So I guess the two most important ones to mention would be Bernard and Salvarani and KineCon and Dietert. I hope I've spelled that right. Who they both showed, so Bernard and Salvarani first showed it for quite a simple kinetic model, and then KineCon and Dietert extended it to a wider range of models that they showed a necessary and sufficient condition for exponential convergence to happen at all. Is that, okay, so the soup over tau of the inf over your xy so this is slightly opaque because I've just written it. So this is the semigroup of the transport. Needs to be strictly greater than 0. So that's basically saying if you integrate your jump rate along the flow of the transport operator, then you're going to have a positive amount. So, you're going to get something strictly positive wherever you start. So there's some time for which you'll get something something strictly positive wherever you start. So that shows that you have some probability of jumping. If you think of these kinetic equations as being the law of a stochastic process, this stochastic process has some positive probability of jumping, of having a collision event or being of diffusing, and that probability doesn't depend on what your initial conditions are. Okay, and so then Moyano and me did this quantitatively. So these previous proofs, they're non-quantitative, you don't see a rate of convergence. And so we did this for some VGK type models, which are more complicated than the original one in Bernard and Salvarani's first paper, but less complicated than the totality of the models they deal with for the necessary and sufficient condition in KineCon and Dietert. Okay, so now I've spent half this, I'm not telling you about the previous work. I will tell you about what we actually did in this paper I'm going to talk about. So we did, I guess what is a very not the most ambitious version of trying to look at this model where you're varying the spatially dependent jump rate. We decided we'd start off with a toy model where we can compute lots of things. So we looked at the Goldstein-Taylor model, and we introduced this spatially inhomogeneous jump rate. So we have two unknowns, u of x and v of x. X is in the torus. If length 2 pi. So u is the density of particles. With velocity +1. And v is the density of particles Oh, sorry, they're not in the torus of dimension D. They're in just the 1D torus. That looks like a so V is the density of particles with velocity -1, and the equation looks like this. So the U particles have velocity +1, and then they switch velocities with rate sigma x over 2. And V particles have velocity -1, and they're transported with that velocity. And then they also switch velocities with rate sigma over 2. So if sigma does not depend on x, then this is very simple playground kinetic model where you can compute everything, you can solve it by Fourier transform, and you can do anything you want to find out what you have about the model. When sigma depends on x, it's a bit more complicated. It's difficult to do lots of things explicitly. A nice property of this is that we can relate it to the 1D damped wave equation. So if we write rho is equal to u plus v, j is equal to u minus v, then you can just check that we get that d2 t squared j is equal to t2 x squared j plus sigma x of j. And this more or less tells us, you know, if we have a solution to this damped wave equation, we have a solution to Goldstein-Taylor and vice versa. More or less, I mean, you have to integrate to get to Goldstein-Taylor from the damped wave equation, but I guess the technical details there are very boring. Okay, so this gives us a tool for, so this, have you got a question?
Yeah, what's the assumptions on the regularity of the sigma?
Oh, so we need it to be in C1. We need it to be continuous, but that's really just for existence of solutions. We work with it kind of in ad infinity. But yeah, I think that's right. Yeah.
Yeah, more technical, but this.
Yeah. So
also never quite optimized.
No. So yeah, I mean, you need if it's just in ad infinity, maybe it's not. Okay, no, maybe it's just an ad infinity. We don't need anything else. Okay, anyway, sorry. Basically ad infinity, but maybe we need something for existence of solutions. Just, you know, to check you have a properly formed stochastic process. So nothing to do with really the long time behavior stuff. Okay, so the reason it's nice that we can turn it into this damped wave equation is that control theorists a while ago, so like Libo has proved various things about this equation. And there's a paper by Cox and Zuazua, which we use quite a lot, which does a lot of precise work with not this equation, but a similar one. So we can go and kind of, by looking at kinetic models that we can relate to a damped wave equation, we can see what people who were doing control theory of damped wave equations 30 years ago have done with similar kinds of problems, and find out the information they have and how it might play in the world of kinetic theory. So that's basically our one of our big motivations for looking at this. Okay, so what kind of behavior do we expect? So like locally, when sigma is small, then the rate of collisions is limiting the total rate of convergence to equilibrium. So I mean, saying this locally, it's a bit it's a bit woolly, but you know, when sigma is small, you are not colliding very much, so you're not diffusing at all, you're not converging to equilibrium. When sigma is large, you're colliding very fast, so you're thermalizing in velocity very fast, but you're changing direction a lot. So you're not moving about the space very fast. If you start with a very concentrated initial data in X, then it's not going to spread out. It's going to spread out very slowly. So when sigma is large, the X process looks like a diffusion with diffusivity 1/sigma. Okay, so if you just look amongst constant sigma, you can easily compute the rate of decay, at least if you're happy to just Fourier transform and hope everything is okay, and you get a graph that looks like this. So if this is rate of decay, sigma. So what was not clear to us at all when we started doing this is whether making sigma inhomogeneous, making it larger in some places and smaller in other places could actually speed up your rate of decay, because when sigma is small, you're traveling in some direction or another, so you travel quite fast into a place where sigma is large and then you jump. So you don't necessarily need sigma to be large everywhere to produce fast rates of convergence to equilibrium. And we were hopeful that, and in fact, if you Fourier transform this equation, you get modes that decay at different rates, and this sigma of X will turn into a convolution function, and you see a mixing between fast modes and small and slow modes. So we thought you might get some kind of enhanced dissipation type thing. We had great dreams, but sadly, they were not true. We have not revolutionized the world of MCMC, otherwise, yeah. Okay, so it turns out that sigma as a constant, a particular constant 2, is the an optimizer. We don't know it's unique, I suppose. We didn't prove this. An optimizer for the rate of decay. So we got this by proving 2 bounds which correspond to different regimes for the L1 norm of sigma. So
sorry, does it depend on which norm you're considering? I mean,
we only did this in L2. Oh yeah, so I don't know if it depends
but
on
you
which
would
norm.
expect that it's the same for L1.
I think so, yeah. I mean, we had some heuristic arguments for why. Originally, we had some heuristic arguments for where it was true in total variation. And then we could prove it actually in L2. So we expect it's the same for any strong. Maybe Wasserstein, it's different. I don't know, probably not. I don't feel like I'm sure that it's, you know, if you take a really weak norm, that it's not going to be different. But yeah, so we prove 2 bounds. So if the L1 norm of sigma is less than 4 pi, then the decay rate is bounded by the L1 norm of sigma over 4 pi. And if the L1 norm of sigma is bigger than 4 pi, then the decay rate is by the L1 norm of sigma over 4 pi minus the L1 norm of sigma over 4 pi squared minus 1. Okay, So this in fact shows that for any given L1 norm of sigma, if you fix the L1 norm of sigma, the constant, you can check that the constant sigma with that L1 norm achieves this bound. And so you can't do better than a constant for a given L1 norm, and you can just pick the constant with the best L1. It's, yeah. For me, this is a really sad theorem. But we actually think maybe that this kind of, I mean, I guess this suggests to me that adding local oscillations into your jump rate is not going to do anything to, we're not going to get some kind of nice, mysterious extra dissipation appearing from this, which we really hope. But when you have a more complicated kinetic equation with a boundary or with a confining potential, I think you know, what we've been looking at, it's not at all clear that a constant sigma will then be the best rate of convergence to equilibrium. Like in particular, I think we kind of believe that having, if you have, say, a confining potential, then having your jump rate get smaller and smaller and smaller as you go off to infinity might give you a faster rate. And there are some stats papers where they are wanting to do this kind of a Markov chain Monte Carlo scheme, and they do some numerics, which shows that at least for their test initial data, you will get a faster rate if you jump less when you're far away from the center of the space where your mass is expected to concentrate at equilibrium. So we're hoping to look at these more complicated settings. So we proved another theorem in our paper, which about the kind of local behavior of eigenvector eigenvalue pairs when you have a single a eigenvalue that's that corresponds to a simple eigenvector. So it's like a single eigenvector, a simple, you know what I'm talking about, a simple eigenvector. So we proved that if sigma is optimal, then the spectral gap cannot be determined by a single eigenvector. I think, in fact, I have to check this, but we didn't put it in the paper. If you have two conjugate pairs of eigenvalues, that you also our characterization of how it changes would mean that it couldn't be determined by two. If you have two like conjugate pairs with different eigenvectors for them. Okay, so we did this by a perturbative argument. So basically, if you look at so if we call a sigma v the operator that's like minus dx of u then if uv is eigenvector with eigenvalue lambda, then we have a sigma uv is equal to lambda uv. So then if we look at sigma going to sigma plus epsilon eta for some small epsilon, eta another an infinity function, then we can differentiate this. So just, I mean, formally we didn't, we have a proper proof, but so if you suppose that you will have a kind of continuous dependence of your eigenvector and eigenvalue on this parameter epsilon, which you will if you start with a single eigenvector, then so if I call this u epsilon, v epsilon, you can just differentiate in epsilon. And you get A prime minus lambda prime U epsilon, B epsilon is equal to A minus lambda U epsilon prime, B epsilon prime. And then if you now test against a solution to the adjoint equation.
I mean, A is sigma plus epsilon beta, so lambda.
Oh yeah, sorry, I don't know where that came from. Thank you.
So the other numbers are lambdas, right?
The other lambda is the eigenvalue.
Okay.
Yeah. So then, if we just test against something, so we can see that a sigma of u v naught bar u naught bar is equal to lambda bar v naught bar u naught bar. Sorry, a star. So the adjoint in L2. So just because the adjoint just flips around your velocities. So then you can test against this v naught star, u naught star, and you will then end up with this right-hand side disappearing. So you get that A primed u naught, v naught bar, u naught bar is equal to lambda primed u naught, v naught bar, u naught bar. Okay, so you just need to check that this will be non-zero. It will when you have a simple eigenvalue. So that's a bit, I mean, it's a bit more fiddly to explain why. So then you can compute exactly what A naught prime is. It's just, so A sigma prime is equal to eta of x times of u would be, sorry, I'm making a mess here. U minus v equals u. And then you can plug this in and you can see that lambda primed is proportional to is equal to minus c, which depends on how you choose your eigenvectors, but you have to fiddle around a bit to find out what it is. Something that looks like this. Eta of x. So provided this is not identically zero, you can choose eta of x to make this be positive or negative or whatever we want, which shows that we can't have been at an optimal sigma if we had a single eigenvector. So if our spectral gap was determined by a single eigenvector, we can perturb our sigma of x a bit to increase or decrease that eigenvector. So it can't have been optimal. And I guess this kind of leads us to, I don't know, a very vague conjecture, but I mean, since this is a kind of specialist audience, maybe it's interesting because you get, so I mean, there's some natural degeneracy that comes up in the equations, but you also get a doubling of eigenvectors when you have kind of symmetries in your equation. And in particular, with a constant sigma, the Goldstein-Taylor has a kind of shift invariance. And we find that having shift invariance of your sigma is always going to improve your rate of convergence to equilibrium. Okay, so we have a kind of, don't know, conjecture is maybe strong, sub-conjecture that the optimal sigma will always have same symmetries as the equation with constant sigma. So I mean, I kind of really want to know whether this is true. So if anyone has any ideas for how to work it out. So we have a couple of reasons for believing this. So the first is because when you do this perturbation argument, you show that you need some kind of degeneracy to produce the optimal. So, and this degeneracy will, okay, having a sigma which is very symmetric is neither necessary nor sufficient to having doubling of eigenvalues, but they tend to coincide. There's reasons, you know, either your eigenvalue has to be symmetric or you have to have two. Eigenvector even has to be symmetric, or you have to have ones that will reflect all the symmetries that you have. Also, maybe more concretely, so I said we looked a lot at a paper from Cox and Zoezua about the damped wave equation when you are pinned at both ends. It doesn't correspond directly to a kinetic equation. So when you have fixed boundary conditions, and then you are able to, so then you have breaking of the shift symmetry. And in that situation, you're able to produce as fast as you want rate of convergence to equilibrium, I think. So they have a kind of breaking of the symmetries in their equation, and they have a very different situation for how to, whether or not you can kind of optimize the rate of convergence to equilibrium. So I guess this would kind of play into the idea about looking at a kinetic version of a Faber-Cron type situation. So you would hope maybe that like a ball is the most symmetric shape there is. Therefore, we'd like to see, you know, if we can work out how to relate the symmetries of the equation to what this optimal sigma is, then I think that would also suggest that you could relate the symmetries of the domain to what, I mean, symmetries of the equation to what the optimal domain is and similar things. And kind of, I guess it's kind of similar to this, like this idea people have with functional inequalities, where they look for whether the optimizers of the functional inequalities preserve the same symmetries as the inequalities. We kind of want to know whether a similar thing is true with these optimizers. And so also whether, you know, if you then have a confining potential, you're interested in the kind of confining potentials that would typically come up in these MCMC type examples are very unsymmetric, because the more symmetry, because, you know, the reason you want to do MCMC is because you have a really high dimensional problem, and if you have lots of symmetries, you can reduce the dimension by looking at the symmetries. So I don't know, I kind of this is very vague. So I'm not sure, maybe it's not ideal for a seminar, but I guess I wanted to say we have this result, which maybe seems quite small, but I mean, I think it's a really interesting question. If anyone, you know, if anyone wants to come and tell us their ideas for how to do this kind of problem, or has any thoughts about it, I think we'd be really interested, because we've been trying this for a couple of years now, not going very fast. Okay, so I think that's the end of my talk. Thank you very much.
Are there any questions?
So I guess you assume that for the linear BGK equation, it would be the same result. I mean, on the torus with the...
Yeah, I mean, we definitely haven't proved that, but I guess I believe that, yeah.
And now let's assume in the one-dimensional BGK equation, you put specular reflection on one end of the domain and diffusive boundary conditions on the other. Does that mean that the sigma then will maybe, because then you would assume maybe it makes sense to run towards that one.
Yeah. So then I think I think that I would guess that you could have you want to go as fast as possible towards the thermal boundary condition in that situation, I think. Probably, I would expect in that situation your sigma is large near the specular end and small near the diffusive end, but
okay.
I don't know. You can probably do numerics there. So then maybe we should. That's a nice.
Can I ask a totally naive question? Can you explain this connection to this damped wave equation again?
Yes. Sorry, I went through this a bit quick. So you just you rewrite it in this u plus v and u minus v, and then you can compute that dt rho is equal to minus dxj, dtj is equal to minus dx rho plus sigma j, and then you differentiate this one in time and differentiate this in x. And substitute one into the other. So you'll get a dtx, d2tx of rho here, and you find it from this.
Okay. You get a dtj there?
So you, sorry, this is wrong. It should be that.
Okay, and there's another question I would have had, why is this a damped equation?
Yeah, sorry. So that was just me not paying enough attention. Yeah,
Oh, okay.
Yes, otherwise, as I agree, it wouldn't be a damped wave equation. Okay, thank you very much.